Hello, everybody. Welcome to the Critical Issues Forum online teachers workshop. Today, we are going to have a second lecture by Dr. Ferenc Dernek-Beres. So he's going to give a lecture on what are nuclear weapons and the effect of the use and the scientific perspective. So he's going to give the lecture on the effects of the use of nuclear weapons. It's a very important lecture for this year's topic on CTBT and nuclear disarmament. So Ferenc, I'm going to give you the microphone.
Okay, I wanted to start with these, with this slide, with these pictures right here. So you see here on the left side, there's a painting by survivors of Hiroshima from the movie White Light, Black Rain, which is a really excellent movie. I very much recommend it. Somehow the artwork can be more powerful than photographs themselves. I find this image really of a mother and a child really touching. So that's on the left side, and I recommend you to watch that movie if you can. And on the right side, there's a picture of an older woman who's lost somebody to cancer. And these are and this is at a nuclear test site. So there's the two different sides here, where in the left side, I'm talking about the first combat use of nuclear weapons. And on the right side, I'm talking about the effects of nuclear testing. And this was actually, I think, at Semipalatinsk, a nuclear test site in Kazakhstan that Masako and I had the honor, I guess, to actually visit. That was very exciting, important. Okay, here's the outline. I'm going to give a gentle but kind of long introduction to radioactivity. Some of this we covered in the first lecture, but I thought I'd go through it again. And then what I'm going to go through in some detail, what happens in a nuclear explosion, which is not always covered a lot. So I'm just going to go into some detail, and that will help you understand some of the effects of nuclear weapons, where they come from, and so on. I'm going to talk about blast effects and talk about thermal effects, then radiation effects, and then I'm going to talk about what happens if you have, basically what is the effect on the environment. And this is about recent research, which I touched on in the introduction for my first lecture, on the nuclear winter, nuclear famine. We realized that now, because of all the research that's being done on climate change, the incredible computing power that they have now, they're able to use the same machinery to estimate what would happen if there would be multiple nuclear events. So we're actually talking about a very small nuclear exchange and what would be the effect on the environment, and we'll find out it's very, very dramatic. And that's just a small nuclear exchange. Okay, so a gentle introduction to radioactivity. Radioactive materials, when something is radioactive, it means that the isotope will over time decay to a more stable form. So you see that here, an isotope decaying from one isotope to another isotope. It doesn't disappear, it just goes from one isotope to another isotope. And as it does that, it releases particles or little bundles of energy. These little particles carry energy. This could be a fast electron. This could be a fast helium nucleus, or what's known as an alpha particle. This could be a fast neutron. This could be a gamma ray, which you know can do a lot of damage. Or it can split and fission, and we talked about that before in the previous lecture. Now, isotopes come in many different flavors, and I kind of show that here with the different types of milk that you might have. You have skim milk, you can have 2%, you have 1%. In the end, it's all still just milk, and that's the fact that the chemical form, chemically, it still behaves just like the element does. So milk is milk. So hydrogen is hydrogen, and if you have deuterium or tritium, it'll still chemically behave just like hydrogen would. But the isotopes themselves have different nuclear properties. So some of them are going to be very radioactive, and when they're radioactive, they can actually cause a lot of damage, which we'll talk about. It's the bullets that cause damage, actually. So here, the idea of radioactive decay, you start out with a certain quantity, then you have a half-life that's associated with that particular isotope. That will decay, and convert to another isotope. And then that may decay as well. And that may decay and so on and so on and so on. But after one half-life, half of the material is decayed into another isotope, and half still remains. And if you wait another half-life, then half of that decays, and so on and so on and so on. So after many half-lives, that isotope starts converting into another isotopes, which may or may not be radioactive. Here are some examples of half-lives. Iodine-131, which is something that we're concerned about immediately after a nuclear event happens. It's got a half-life of 8 days, so that's very short. So if you wait a few weeks, or a few months, then the quantity of that is going to be so many halves, so it's half times half times half times half, that it's going to be, down a large quantity. And here, strontium-90 and cesium-137 is another two isotopes that we really are concerned with, which stay around for a very long time. So this material can get into dust and dirt and so on. And as I always say, the kids, they eat the dirt, and then that, it's very, very dangerous. Whereas plutonium-239, another isotope that we talked about in the previous lecture, has a half-life of 24,000 years. So it's a very big range in half-lives for the different isotopes. And it really is like alchemy, as I said before in the previous lecture. Cesium-137 converts and decays to barium-137, which is a completely different metal. So if we wait long enough, then most of it, the cesium-137 will actually decay to barium, a completely different metal with completely different chemical properties. And I kind of look at this as kind of like buckets. And so cesium-137 has a very small spout because its half-life is 30 years. So it's very thin, so it dribbles into the next bucket. And then the barium-137M, this is called metastable state, or very short-lived state. It has a very thick spout, so it immediately goes into the next bucket, which is barium-137, which is stable, so there's no spout. So you can really kind of think of this in terms of buckets. Whoops. Now, these particles can be very useful, or they can cause a lot of damage. So I call these bullets because that's really how you can think of it. So if you think about a gun, shooting bullets, it can cause damage. These little bullets can cause damage to the body, but at the same time, it's the exact same bullets that allow you to do diagnosis and imagery of cancer and so on. So you kind of have to think of it as kind of a double-edged sword, where the radioactive sources can cause damage, but at the same time, they can be very important for medical reasons, for many other reasons as well. It can also be very useful. Okay. So keep in mind the idea of energy being carried by particles. The more energy that you have, so here I'm representing that by having two separate bullets, a small bullet and a big bullet. So a bigger bullet means really the bigger energy. The more damage you can generally do. And the more bullets you have, the more damage as a whole. So really that means that if you have an isotope, you have a large quantity of the isotope, then you'll get more bullets coming off. If the half-life is shorter, then also you get more bullets coming off, so then it's more dangerous. This kind of thing that you have to keep in mind of these particles kind of being like bullets. There's many different types of bullets, as I already mentioned. You can have alpha particles, and these are easily stopped by just a piece of paper, but then beta particles will go through wood or something like this, so these can get through. And of course, there's gamma rays, which can go through directly through metal, and goes through the body. Can cause a lot of damage. Now, excuse me. The more bullets you have, the more damage you have. It tends to be measured in what's called becquerels or curies. So becquerels is the number of decays per second, and curie is another unit. I think it's 7.3 times 10 to the 10 decays per second. This is how many decays you get from the particular isotope. Now, the different particles can cause damage in different ways. If you have the alpha particles inside, which I'll talk about, if you have an alpha particle emitter inside your body, even though it's easily stopped by paper, if it's inside your body, it can do a lot of damage, with, can damage the soft tissue. And but whereas gamma rays will just kind of have a track through the body and will release the same amount of energy or deposit the same amount of energy as a function of distance along the track. You need special sensors to detect these sources. This is one of the things that are might make radioactivity such a complex thing, is the fact is you can't really, or not complex, makes it scary for people, is the fact is you can't see it, you can't taste it, you can't hear it. It's not like other dangers that you have, let's say, a big wave coming at you or something. You can see it, you know what's happening. Whereas with radioactivity, that's much harder, because we don't have ways of sensing radioactivity necessarily, at least very smaller doses. But the smaller doses can still do damage, as I'll talk about. There's the last thing, which is the fission process, which we talked about before. This is the nature of nuclear reactors, the energy for nuclear reactors, but also nuclear explosions. So if you think about coal burning itself, producing about 18 electron volts. Don't worry so much about what that means. Electron volts is just a unit of energy. 18 electron volts per atom burned. Whereas if you have one fission, you have 200 million electron volts per fission. So it's a very, very different energy scale. And this is something we've talked about before, but what happens is through the fission process, you split something like a uranium-235, and it can split in many different ways. So here, for example, I'm showing carbon-11 splitting and radon-222 splitting. So it just splits in many different ways. And this, of course, is radioactive. Radon-222 is radioactive. Carbon-11 can be radioactive. So what's left behind is, I'm not sure about carbon-11 being radioactive. I have to think about this, but what's left behind is radioactive isotopes. And you could have hundreds and hundreds of different radioactive isotopes. Now remember the buckets. Let's look at the complicated case of radon. Radon-222 has a 3.8-day half-life. When it decays into polonium. And then some part of that, there will be some percentage associated with this, will decay to this isotope. And some percentage will decay to lead-214. And then you get other types of isotopes that it will decay to, and so on. So you get this picture that you should have is nothing simple, but these buckets, goes from one bucket to the next bucket, to the next bucket, to the next bucket. And each time it does that, it releases these particles, which are like bullets. So just from one decay of radon-222, you can produce a lot of buckets. Now there's really a few different types of exposure that you should think about that's dangerous to the body. And the same is true for radiological dispersal devices. So what's called dirty bombs, where you take radioactive materials and you explode it over a large area. The danger is that the material could be ingested, in which case it goes into the body and does damage there. It could be inhaled, which you can see here, it could be inhaled. And then the other type of exposure is called external exposure, where you secretly hide, for example, here you have an isotope here, and you're irradiating people just from a distance. So those are the three different types of ways that you can get a serious dose of radiation and cause damage to your health. Now, the types of damage to cells are called deterministic and stochastic. These are two types. Deterministics is very short-term, very high dose of ionizing radiation. The effect increases with the dose. You get something called acute radiation syndrome, where you can get very serious health effects and even death if the dose is very high. So a lot of this we learned from Hiroshima and from other cases where there have been very serious incidents. And the stochastic effect is over a long time increased risk due to cancers. And this is more a probabilistic effect over population. So you can say overpopulation, you can kind of predict that overpopulation, you would get so many cancer deaths if the population had so much dose, total accumulated dose. But the idea here is that no threshold exists. Whereas with deterministic, there is actually a threshold at which you get ARS. Whereas with stochastic effect, there's no threshold that exists. It's basically, it is connected to how much dose you have, but just because you had a high dose doesn't mean you'll get cancer because of that. You get increasing cancer risk. And the increased cancer risk is higher for women than for men, and also higher for children. That's what I show here. You can see the percentages here. It's slightly higher for, this shows you this 100 centigrade. So gray is a unit of dose, sort of dose. And you see that the percentage is slightly higher. Now, the important thing is this is called a linear no threshold model. And this is what I just kind of described briefly. This is a model that tries to associate a risk with a dose over a population. So we know we have data, we have an increased cancer risk according to a high dose, which I show up here, which is measurable from cancers from Hiroshima, Nagasaki, Chernobyl, etc. We know generally that you can assume that at 0 dose, you get 0 cancer risk. But we don't know what's happening in this region here. At very low dose, it is reasonable to assume that you have a certain cancer risk, but since the dose is so low and so many people get cancer, it's very difficult to make a cause and effect to be sure, to know exactly how this curve behaves. It's very, very difficult to measure it. And many people have tried, and it's a very active area to try to measure this. This is important because it's, if you're living close to a nuclear power plant, for example, then you get a very, very low dose. And so the question is, what's the cancer risk if you live close to a nuclear power plant, for example? Or, another type of facility. This linear no threshold model is basically what regulators use as a way of assessing risk. It is the most reasonable, but it's also very controversial. You have to have some kind of measure of risks. This is one way to measure it. This is what the regulators tend to use. But we really don't know what happens. The curve could go up like this, or the curve could go down like this. We really don't know because it's so hard to measure in this area. And this is actually a very controversial area and an area of a lot of research. As I already mentioned, alpha emitters are particularly dangerous. This shows a picture of Alexander Litvinenko, who's a Russian spy, or a former spy, sorry, who was poisoned with polonium-210. And this is what he looked like before, and this is what he looked like only 23 days later. So the effect was very dramatic and very fast, the effect of the polonium-210, which is an alpha emitter. To summarize, prompt gamma rays and neutrons will come from the fission process. This is important when we talk about nuclear weapon effects. The betas, gammas, and alphas will come from radioactive decay of the fission products or induced radioactivity, which we'll talk about a little later. Particles are like bullets, damaging the body. If you have a dose which is higher than 1 gray or 1,000 centigrade, sorry, I think that's not. I think there should be 10,000. I'm not sure. But if the dose is high, then it could lead to ARS or this acute radiation syndrome. If you get a really, really high dose, it could even lead to death. If you get a slightly lower dose, then there's things that you can do medically to try to become healthy. And the particles exposed to the population causes the increased cancer risk, but this also depends on dose. And as I said, this linear no threshold model is a way of trying to measure or trying to associate the risk with low dose radiation. Is something that's actually quite controversial, but is generally used by all regulators. So now back to nuclear weapons. What happens in a nuclear explosion? Well, in a nutshell, All damage stems from the energy released in the explosion, which is converted to these particles or bullets, light or objects. So the particles or light, they carry energy, and this gets transferred to objects, and that heats the material, or it hits the material and can do damage that way. You have to think of these particles as energy packets and delivering energy. Energy is transferred to objects with devastating consequences. And I want to remind you of these important things. The more energy you have in the particle, the more damage you can do. And the more bullets you have, the more damage as a whole. So particles like bullets can hit cells, objects, and damage them. And the particles can transfer energy and heat objects. Now I kind of show you these two types of particles, and really they're very much connected, but nuclear radiological material particles, so these are the alpha particles, the neutrons, the beta particles, and the gamma rays. The gamma rays stem from nuclear events and nuclear reactions, but it's also electromagnetic radiation. And that's what I'm showing on the right side. Is you can have visible light, you can have infrared, you can have X-rays, you can have UV rays. All these things can do damage. And all these things happen from nuclear events. So now we're going to go into some detail about what happens during a nuclear explosion. Now, 1/1,000,000th of a second, all the yield that you have. So nuclear explosions are measured in terms of TNT yield. So it's measured in terms of what would it be equivalent to if you had a conventional explosion of TNT, just TNT explosive. So when we talk about 1 kiloton, we're talking about 1,000 tons, an equivalent explosion to 1,000 tons of TNT, or 1,000,000 kilograms of TNT. So you may remember the picture that I showed you guys in the very first lecture, where I talked about the nuclear difference, where I had the one side, I had a picture of Hiroshima, on the other side, I had a 1 kilogram explosion. So you really get a sense of that, how dramatically different the range in energy is. Okay, so it's 1/1,000,000th of a second. All the yield is deposited in bomb materials. You get heating to 10 million degrees Kelvin, which at this level, 10 million Kelvin is the same as degrees Celsius. We're talking about extremely hot temperatures. All heated objects emit radiation, which is related to the temperature, and that's what I kind of show here. This shows you the wavelength, so it's wavelength of light, and this shows you the power, but really it's showing you the temperature here, and for different temperatures, you have a different peak wavelength, and at this kind of temperature, you're in the area of X-rays. Now, fundamentally we think about X-rays as being very penetrating, but at this level and at this density, it only travels a few millimeters to a couple of meters, so it doesn't travel very far. So you're thinking of this at 1/1,000,000th of a second. This ball of energy is very small, and it's generating X-rays and so on. Now I want to talk about the story of the tortoise and the hare. There's two expanding spheres that I want you to keep in mind in a nuclear explosion that can cause damage. Keep in mind the story of the hare. Of course, the story is, and I don't know the whole story, but the idea is that the tortoise and the hare start at the same time, and the tortoise here represents the debris sphere. So this is all the bomb materials that have been produced. So all the fission products and so on. And later on, I'll show that as a red ball. And then the hare is the X-ray sphere, which of course, travels very fast because it's light, which is a dashed ball. But at one point, you'll see that the tortoise will overtake the hare. So keep that in mind, these two things. Okay, so at the very first level, we're talking still very, very high temperature, tens of millions of Kelvin, very short amount of time. This is almost immediately after the bomb happened. We have the debris sphere and the X-ray sphere, which is already quite far out from where the debris sphere is. And you have enormous pressure here in a very small space. You can imagine you have all this energy sitting in this very small space, and the debris sphere is just about to expand outward. The X-rays, of course, travel much faster. So you have these two separate spheres that are carrying energy outward. But again, the X-ray sphere expands much faster. And 70 to 80% of the energy is converted to X-rays. The rest is kinetic energy, so that's the energy of motion of the vaporized material and the debris. Now the X-ray sphere is expanding by what's called radiative transfer. It sounds complicated, but all it's doing is the X-rays are being emitted, then it gets absorbed, and then it gets re-emitted, and so on and so on. So it starts to expand fast, but not at the speed of light. The sphere itself is not expanding at the speed of light. Once the air is ionized, meaning that you strip the electrons from the atoms, it becomes transparent to other X-rays because it can't absorb because there's no electrons left. So the X-rays start to go faster, and so the expansion increases. So that's why this X-ray sphere here is shown further away from the debris sphere. But the debris sphere at one point is also going to, because it's a shock wave, is expanding faster than the speed of sound. It travels outward, that's called a shock wave. And after 300,000 degrees Kelvin, the speed of the expansion of the isothermal sphere, and that's the X-ray sphere, slows, and the debris wave, which was the tortoise, overtakes the isothermal sphere. So that's this picture here where you have the tortoise overtaking the sleeping hare. And this is what happens here. The debris sphere starts overtaking the X-ray sphere, which is starting to cool and slow down. The debris sphere expands further outward and moves rapidly past the isothermal sphere. And the blast wave, the air starts to glow. The debris material shock wave, because it's such a high temperature, starts to glow brilliantly. The isothermal sphere, which is the sphere that was inside the dashed light, you actually can't see it. As the shock front sphere expands, it cools and becomes less bright. And the brightness is now about 1% of the total thermal energy of the bomb. And this is the first pulse. So the first pulse is really the debris material shock wave that's generating all this light. Now the debris shock wave starts to cool down to something like 3,000 degrees Celsius. And then the isothermal sphere starts to become visible. And the debris shock wave stops glowing and becomes transparent to the much brighter isothermal sphere, which glows at 8,000 degrees Celsius, which now is actually glowing in the infrared. If you think about it in terms of heating iron to a certain temperature, then it starts to look red and also starts to glow in infrared. It's cooler, but it's still bright and shines longer than the first pulse, and 99% of the thermal energy is in the second pulse due to the brightness of the isothermal sphere. So you really have two peaks that are happening, or two spheres that are shining brightly. The debris shock wave does not glow, but continues to travel outward. And the light from the isothermal sphere is now visible and also glows in the infrared. And it's heating everything. And it's thousands of times brighter than the sun. And in fact, this can cause flash blindness many miles away. So the picture that I wanted to have is kind of two pulses that are happening, two bright pulses that are happening. One pulse is due to the heating from the debris itself, the fireball. And then the second pulse is due to the X-rays, which are an X-ray sphere, which is now converted to infrared. So you get two different pulses. One is pulse one, which is at a certain time scale, which is more like less than a millisecond. And then the second pulse, and this is what I'm showing here in terms of time, and it's logarithmic. So because 10 microseconds, 100 microseconds, 1 millisecond, 10 milliseconds, 100 milliseconds. The second pulse is when the isothermal sphere, so this is X-ray sphere that is now converted to different wavelengths, starts to glow, starts to be visible. And so you get this kind of two peaks. And these two pulses are actually exploited for nuclear explosion detection by the Vela satellites. There's satellites which use something called bang meters. and it's actually measure measure this light curve and to determine what the yield is, because the time that this first minimum happens in this pulse here it actually tells you about the yield, and the second maximum also tells you about the yield. So you get kind of consistent equation between the two, and you could determine the yield of the explosion based on looking at these pulses. So you could actually detect that in space. This actually happened. There was a mysterious event. So this is a way of detecting, determining the yield from nuclear explosions. But there was actually an event in 1979, which people really don't know whether it was a nuclear explosion or not, whether it was perhaps there's been there's a lot of speculation about whether it was South Africa testing for Israel a nuclear explosion, or maybe it wasn't a nuclear explosion at all. And this is what it looks like. And I actually looked at this in some details. That's why I'm kind of showing you this. Is you get these two peaks that you have, which look very much like a nuclear explosion. But then again, if you start to look at other nuclear tests where they should be in this band here, the first peak is exactly where you expect it to be, but then the second peak sort of does something funny like this, which we don't really understand. So we don't know whether this event was really a nuclear explosion or whether it was something else. We really don't know. So there's some mystery around this 1979 event. Okay, just to continue, we talked about the fact that you have these two kind of pulses that you have. You also have the radioactive cloud. So this is debris that comes, the bomb debris, and it rises high into the atmosphere. And depending on what the yield was, it rises higher and higher and higher. And then you also have the rise of the fireball. So if this is actually happening as a, the explosion is not on the ground here, but is actually higher up in the air, which produces a higher effect, which I'm going to be talking about, then that ball actually rises very fast to the top at something like 200, 250 miles per hour, just like a hot air balloon. So the general nuclear bomb explosion, this is kind of a rule of thumb that people use. 35% is the thermal energy that's released, and this is electromagnetic or EM radiation. 50% is the blast wave, which is coming from this debris shock wave that travels outward that I talked about. So that's a vast amount. And then 50% that's left is coming from nuclear radiation. 5% is from the prompt neutrons and gamma rays. And the rest are going to be, all the isotopes that are still decaying time after the explosion. And the total energy, as I said, is a TNT yield of the bomb. So Masako, I thought I'd take just a break for questions if people have them.
Ferenc?
Yes.
Okay, so you want to get break. Actually, so this is for the sake of teachers who are going to watch the video. At this point, I don't think there's any teachers.
Yes. Okay.
I was actually, I have a question. I think you talked about the difference between deterministic effect and stochastic.
Yes.
So you said there's no threshold, and I think this concept is kind of interesting. So, for example, a detonation for the nuclear testing.
Yes.
Usually, detonation for the nuclear testing is going to be conducted in an inhabited area. But sometimes, it's not the case. So that's why we have a lot of problems. So you think the effects like of the nuclear testing, like a semi-Palatinsik or South Pacific, is going to be the category of a stochastic effect, or am I?
Yeah, that's right. That's exactly right. That would be in the category of stochastic effect. So it's longer term, hard to measure. And the reason why it's so hard to measure is because it's because everybody gets cancer for many different purposes. But if you see an increase in the rate of cancer, it could be due to this, but it could also be due to other purposes. But you're right. That's how you measure that's right. And that it would be the stochastic effect, not the deterministic effect.
Right. Yeah.
So in the case of, people who had a direct exposure, that would be the deterministic effect, where they would get, their whole system would shut down essentially.
Mm. So for example, the black rain, the rain in Hiroshima and in Nagasaki, I think it was mainly in Hiroshima, the people who came to the area, they got a lot of black rain and they died a few days after because of radiation. So the black rain, the effect is perhaps this is
deterministic
effect.
Yes, absolutely. So Masako, you can really think of it in terms of time. Stochastic is really over. Deterministic is it happens very quickly, whereas stochastic it would have it's statistical over a longer period of time.
I see. Okay.
Thank you. 10 years and decades.
10 years. Also, it may also include some generations to generations, like.
Yes, although I'm not an expert in that. I don't.
Yeah.
I haven't looked at that.
Mm. Yeah, because in the effect, there are many different ways to be exposed to radiation.
So,
like
that's very important you pointed out, because that builds to the stigma, right? Of survivors.
Right. Yeah. So when we listen to the testimonial of the atomic bombing survivors, many of them have experienced like a discrimination, especially when you get married.
That's what I want to say.
Because of the exposure to radiation. And some people actually, at the early stage of the experience, people had some wrong concept that radiation is contagious, which is not.
Yes.
So it's
That's
a very big difference from for example, biological weapon, like Ebola, those are contagious. But since that was the first time, people really didn't know if it was really contagious or not. So there are many that kind of hardships that people, atomic bombing survivors, underwent. So that is also very important impact of the use of nuclear weapons. Yeah, thank you. So at this point, I do not have any additional questions. So maybe by the end of your lecture, we may have some teachers who are going to join. Let's see. So shall we continue?
Yeah, sure. Okay.
Thank you.
Okay, so I'll just continue. So now I'm going to talk about the effects of nuclear weapons in more detail. I'm going to talk about the effects of blast waves. So here you see, this is a ground explosion, and you see how this shock wave is moving outward. And if you look really small, really carefully, you can see this thin line here. And this is the shock front as the material, as it expands outward. And the way you can think of it is everything that's in front of the shock front here hasn't actually seen the effect of the nuclear explosion yet, in some sense. So that's why you have this very strict kind of barrier between where the shock front hasn't hit yet and where the shock front has hit. Think of a bomb kind of as dropping a stone in a quiet pond. The waves will travel out in concentric circles and disturb the water. Of course, the difference is it's not like a continuous wave where you have a, one wave after another wave after another wave after another wave. It's more like a tsunami, one big wave which comes in and does a lot of damage. The shock waves travel out and compress the air. As you can imagine, it has all this energy and compresses the air. And the effect of that compression is measured in PSI, or pounds per square inch. Now I'm showing the effects of a blast wave. Here you can see what a particular location would experience as a function of time. First, the detonation happens. There's a certain distance that this house and this tree is away from where the explosion happens. So as the explosion happens, of course, the effect hasn't arrived at the house yet. But then as time continues, that's here actually, as time continues, you get the wind that actually happens. So what the two effects of this blast wave is that you get I'll talk about it briefly, is an overpressure, so increase in pressure, local pressure, and then you can have a kind of a very strong wind, which you associate, you see all these, whenever you have a large explosion, you get this kind of wind that travels out. That's actually the blast wave that comes out. And so in this case, a certain distance, first you have the wind going this way, and then there's a period of when the first part sort of passes, the blast wave kind of passes, and then a few seconds later, or a little bit of time later, then you get a negative wind, which actually pulls you back into where the detonation happened. And of course, that causes even more damage. The blast wave travels outward and pushes the air outward and compresses it. The compression air creates a front, which causes two effects. First is called static overpressure, which increases the local pressure of the moving front, which is kind of like a tire running over your hand. The body is quickly squeezed inward, like diving too deep. I kind of think of this as kind of a crushing effect, whereas you can have dynamic overpressure, which causes a very high speed wind. Now this wind is higher than anything. You really have to look at this, right? We're talking about very, very high winds, like 900 miles per hour, way higher than any hurricane. And of course, you have to think of it this way, that when you get such a high wind, it destroys everything, but it also takes that wind energy into objects, and that objects actually travels very fast and can hit people and can hit different things. So the energy is carried into objects. The objects travel very fast and could cause further damage. So it's not just the wind carries objects which do the damage. Now pressure as a function of distance is related to the yield. So as you get further away, then the pressure that you get is going to be less, the effect is going to be less. Hardening a silo, so hardening a building or a missile silo means that you harden it so well that you have a certain pressure that's needed that can withstand a certain yield. So as I say, it's 20 PSI or something like this. You actually harden it so it can withstand that kind of pressure. Now let's talk about this a little bit more detail. This is this example that I talked about in terms of one wave that's traveling out. So T1 is a time period which is less than T2, which is less than T3, which is less than T4. And so this shock front just moves outward like this, like this, like this, and it actually reflects off here and interacts with the original shock front as it travels outwards. And what actually happens is the two shock fronts combine, and this makes even a stronger, more dramatic effect than the single wave itself. So it's called a Mach stem. It's a combination of reflected and the incident blast wave, and it greatly enhances the destruction. it's kind of like a factor of 1.5 or 2 in distance in terms of you would have the same effect if you wouldn't have the Mach reflection compared to if you would have. I'm going to show you that in a video here now. So this is an NHK video which shows you what the effect is, where they try to reproduce the effect of the Mach stem, which was observed in Nagasaki.
The horizontal blast pressure intensified around 500 meters from ground zero. We filmed that movement using a special device that can detect invisible flows of air. Here's how the blast expands from the center of explosion. When the blast wave strikes the Earth, it is reflected upward to form a second, dome-shaped shock wave. Let's focus on the area where the two waves meet. One shock wave comes from above, as it expands from the core of the explosion. The other is reflected off the ground. The two blast waves then merge, more than doubling their individual pressure, and continue expanding in a horizontal direction. The combined wave grows in height and strength as it moves along the ground. This is the shock wave, known as the Mach stem.
We used a very small amount of explosives, but something much bigger like an atomic bomb or a huge amount of explosives or explosion would have generated the same kind of shock wave movement. The result of our experiment is in line with what happened in Nagasaki, where Mach reflection occurred at a short distance from ground zero and caused severe damage farther away.
So that shows you the effect of what's called the Mach stem. So this is the combination of the incident wave, so that's the first wave that comes out, and then the reflected wave combining, producing a very strong shock wave. Now, I want to show you the effect. It's kind of going to be a theme for the next few slides, which is two very different explosions. So in here, I'm showing you the energy in kiloton TNT. It's kind of just drums it home for a 10 kiloton explosion. See, that's a very thin line here. And now I'm showing it for a 1 megaton explosion, which is 1,000 kilotons. So this is 100 times this. And this is something that I want you to keep in mind, because we're going to compare the blast effects and also thermal effects for these two very different size explosions. Because one might think that the effect of a 1 megaton explosion is going to be 100 times the effect of a 10 kiloton explosion, because it's 100 times more energy, but that is not the case at all, and that's what I want to talk about next. So here I'm showing the effects of a blast wave, the distance in kilometers from the hypocenter where the explosion happened, for that you would get concrete building collapsing or wood frame building collapsing or shattering windows. So these are all correspond to very specific pressures or PSI. So here what you see is that at that a 10 kiloton explosion, the distance of about 1 kilometer away, you would have concrete buildings collapsing. Whereas for a 1 megaton, which is 100 times more, it's more like 5 kilometers. So you might expect that actually the effect is going to be, if it's 1 kilometer here, well, surely it must be 100 kilometers if it's 100 times more energy. But that's not the case at all. And that's something important to keep in mind, that is not a linear effect. The effect is not linear. And I'm showing here, if it would be linear, what the curve would look like, but it's not actually like that. So this is a very important point that I want you to think about: blast wave damages effects are not linear. The damage from a 1 megaton bomb in terms of blast is not 100 times the damage of a 10 kiloton bomb. It's still a very awful, both explosions, but the effect is much less than you might have thought. This is just kind of a quick explanation of why this is the case, and you can of course prove this, but there's kind of an easy way to understand this. Think that the effect of a 10 kiloton bomb is like a small little ball of a certain radius. Imagine stuffing 100 of those small balls into a balloon. The balloon won't expand 100 times the radius, as you know. So you can, so if you have, in fact, the radius expands outward very slowly because it's got to expand in all directions. And that's basically the reason why you don't have, why the effect is not linear. Now I'm going to show you kind of a sequence of these, of an explosion. This is obviously an airburst. First, you get very bright light rapidly heating the house. This is a very short time afterwards. So it's heating the paint here, heating the house itself. And there you can see the house starts to be on fire, but only on this side you can really see that. You see the car here in the background in the shadow. And then the blast wave arrives. So the heating was before the blast wave actually arrives, and this actually destroys the house. Excuse me. You get full destruction of this house in less than 3 seconds. So now let's talk about the effect of thermal radiation, which you saw how it was the heating at the beginning. This can cause very serious burns and cause very serious fires. Thermal radiation is, I mean, you can imagine if you're creating an object on Earth hotter than the sun, 1,000 times brighter will burn everything, like the house. And you kind of have to think of this as these bullets start accumulating energy, and once that energy reaches a certain threshold in a certain little area, it starts to have so much energy, starts to burn that material. So energy flux is the number of photons that hit. So photons are light particles that hit per centimeter squared per minute. It can correspond to an energy which is often expressed in terms of calories per centimeter squared per minute. And you can have different thresholds for different materials burning. Now you have to kind of think of this in terms of what you may have played with when you were younger, which is with magnifying lens. What you're doing is you're concentrating the light. So you have more photons in a very small centimeter squared, a very small little pinpoint. And because you have so many photons, you produce so much energy, it starts heating the materials. It's kind of a threshold for different materials when they start burning. And once you get to a certain, let's say, photon density on that little piece of paper, things will start to burn. And the same is true with other materials like newspaper. Will ignite at a certain let's say, density in some sense. Dry wood, 4 to 8, is usually 4 to 8 cal per centimeter squared. Coarse grass, 6 to 11. So if you have those high fluence, or this high number of particles hitting a certain area per centimeter squared, things will start to burn. The effect, again, is not linear. In the case here, I'm showing again a 10 kiloton bomb and a 1 megaton bomb. You get third-degree burns, which are here charred skin and extreme pain. Here at about 2 kilometers from the hypocenter for a 10 kiloton bomb, and then for a 1 megaton bomb, it's more like 11 kilometers away. And these other effects happen like this. So 1 megaton bomb will give a serious sunburn from 20 kilometers away, third-degree burn at 11 kilometers. So this gives you a sense of the incredible amount of heat that's released during nuclear detonation. And this, as I was saying before, this shows you the explosion yield and the kind of distance from the explosion at which you can ignite grass or different materials. So it means that a 100 kiloton bomb can ignite grass at 3 miles, which tells you how incredibly intense the light is and the heat is. This, of course, can lead to very serious fires, and I'll touch on that later on as well. You can get initial fires, which are started by the thermal radiation, which can combine, the different fires can combine and produce something called a super fire. And then you get high velocity winds, which are directed towards the center of fire, which basically the fire itself produces its own kind of climate. And you get these effects happening. And firestorms developed in Hiroshima about 20 minutes after the explosion. Death was caused not only by the fires, but also by suffocation. People went into shelters, and basically the explosion sucked all the air, oxygen out of the air, and people basically suffocated. Now, if you look at the casualty rate as a function of distance from the hypocenter, the blast injuries very close to where the explosion happened, are very intense. Burns are also very intense, and at one point, you have 50% casualties are due to blast, and 50% due to burns. And as you get further away from the hypocenter, the blast effects become less, and other effects like thermal effects become more important. Now let's talk about the effect of radiation. Initial radiation from the fission bomb, you get prompt gammas and neutrons. They penetrate deep to the ground from the rising fireball, so the fireball rises very fast. You get short-lived fission product decay. You get much less radiation from an air burst than you get from a ground detonation, and the reason is because this air ball moves upward so quickly. So you get a large dose at the beginning, but you might not get all the materials that are left behind, and it's the reason why it's possible to live in Hiroshima now. You get residual radiation, which can be due to what's something called neutron activation, which can produce radioactive isotopes in the rock or dirt. So basically, what happens? You get the neutrons that are released from the fission explosion, and these neutrons change the material itself, the rocks and so on, and make the rocks themselves radioactive. You can also get neutron activation on nitrogen in the air, and it produces carbon-14, which is of course also dangerous because you can inhale it and so on. And then you have the decay of the fission products that are released, which is the fallout and so on, that can travel high in the atmosphere, and can also include bomb debris, which can travel for very long distances. And the fallout patterns, as we know, can be quite complicated. If you think about in terms of Fukushima, the winds changed, and the fallout pattern was very complicated. This can only be really predicted by careful computer modeling. Now, the size of the explosion gives you a sense at how high the fallout will travel. So, as it travels higher, as the cloud, essentially the mushroom cloud, travels higher and higher and higher, it will release the radioactive materials, the fallout, at further distances. Of course, all of this depends on the rain and environmental conditions and so on. To summarize, the effect of a nuclear explosion can be the destructive blast wave, which is intensified by the air burst, as I said, because of this reflected effect, getting the max stem. You can have thermal energy, which can cause burns. You can have thermal energy, which can cause mass fire. You can have initial radiation bursts of neutrons and gammas, which can do a lot of damage. You can have residual radiation, which is the fission product decay, the carbon-14 production, induced radioactivity in the rocks and dirt, so on. It actually makes the material radioactive. And combined with that, you can expect to have little medical response or support. So here I show the effect of a nuclear weapon, just everything, It's kind of a picture of all the things that could happen. Of course, you have blast, you have radiation, you have thermal effects, you have fallout, you have blindness, burns. Area is going to be denied, economic effect, mass evacuation themselves can cause, people can have accidents and so on under difficult conditions. Huge psychological effect, displaced people, many different things. So one of the questions you can ask is, will international organizations be able to cope? Well, there was a very recent study by the Norwegian Radiation Protection Agency, and they found that adequate countermeasures to a nuclear detonation simply don't exist, even given the vast resources that Norway has at its disposal. No official UN organization mandate is to actually deal with such an event, a nuclear event. No specific UN or interagency planning or exercise that have been conducted to prepare for a nuclear detonation. Well, there have been such planning for radiological incidents such as a dirty bomb scenario. So if a nuclear event happens, it will be very dramatic in terms of the response, in terms of the emergency response. And we've yet to really figure that part out. So now let me shift a little bit and talk about the concept of nuclear winter. This was an effect that was discussed back in the 1980s by prolific researchers such as Carl Sagan, and it was really misunderstood. And people thought that the effect actually went away, and that it was, people said it was a hoax, and the effect is really small, and so on. And now with recent research, because of the International Panel on Climate Change, because of climate change research and very sophisticated computer modeling, we can use the same models to predict what would happen in case there would be an exchange of nuclear weapons. The idea is you get massive amounts of smoke and soot from fires that rise in the upper atmosphere. This reflects the sunlight back into space, and you get rapid large drops in global surface temperatures, and you get collapse of basic life-sustaining ecosystems. On that bright note, I'll talk about it in a little bit more detail. Now people tend to talk about a nuclear winter, a nuclear famine, because the famine that would result from this. Recent research is done by Alan Robock and Owen Brian Toon. They looked at effect of a small-scale nuclear war between India and Pakistan. This is where they modeled this. 100 Hiroshima-type weapons, which is, a very small portion of the number of nuclear weapons that actually exist. Imagine a skirmish in Kashmir escalating due to poor communication, misunderstanding, panic and fear. Perhaps this time we're not lucky, because we've been lucky so far with many incidents that happened in the past, which didn't actually escalate into nuclear war. Effects are devastating, at least immediate 20 million deaths. But that's not all. That's not all, and that's what I want to talk about. The massive fires would be produced and would be fueled by winds, as I said, it creates its own climate and so on. You would have 5 teragrams of smoke injected into the upper troposphere. That's what the simulations say. A teragram is 1 times 10 to the 12th gram of smoke that would be injected. You can kind of see that here in this picture, how the smoke would kind of envelop the area. After 49 days, the particles would blanket the inhabited Earth, blocking enough sunlight that skies would look overcast almost everywhere. You can see that here. Looks almost overcast. This is after day 9. This is day 49. And this is what you would see as a function of time. This is the regular, the temperature anomaly or the global warming effect. And you see how it increases as a function of time. Then if a nuclear exchange, as I've been talking about, would happen, you have a dramatic drop in temperature, which would devastate crops and so on. after time, in about a decade, it will start to creep. It will start to creep up in temperature. So the resulting soot cloud would block 7 to 10% of sunlight, leading to significant cooling and reductions in precipitation, lasting to more than a decade. The growing season around the world is shortened, not allowing crops to reach maturity, lead to increase in price of food, mass starvation, hoarding by countries that have funds, disease, war, competition for food. According to the IPPNW, which is International Physicians Against Nuclear Weapons, Masco will correct me, 2 billion people are at risk. So this is a very careful study that was done. Let me continue. That's not all. It's cool, dry, and dark, but also UV depleted. So heating of the smoke particles high in the atmosphere increases the local temperature high up in the atmosphere by at least 50 degrees Celsius. This draws in nitrogen oxides, which depletes the ozone layer. You can imagine at such high temperatures, the chemical reactions are faster, and this produces and basically destroys the ozone layer. And then, of course, you can get damaged terrestrial and oceanic plants and produce skin cancer, ocular damage, and other health effects in humans and animals. Very, very dramatic. This is the effect as a function of latitude. You can see that the higher latitudes have a higher, more dramatic effect as a function of time. This is kind of the global mean, if you can think of it that way. The impact on agriculture is the sudden cooling, less sunlight, less rainfall, shortened growing season, reduced crop yields. Stratospheric ozone depletion damages crops that are sensitive to UV, besides all the other effects that I talked about. Of course, you get disruption of petroleum supplies, effects, use of farm machineries, fertilizers, pesticides, and so on. Radioactive and toxic contamination also takes vital farmland out of production. And then you get potential also the collapse of the global distribution system. So very, very dramatic effect from just a small regional exchange. These are serious scientific studies that were done on what the effect would be done and on very well researched, very well understood computer codes. There are, of course, some still questions about the studies. But generally, as far as I understand, most people think that this is uncontroversial in terms of what the effect would be just from a small exchange. So when we talk about nuclear weapon effects, we have to also consider the environmental effects. So just to summarize, we get the effect of multiple nuclear weapons are catastrophic and dwarf that due to global wars. The effects are sudden cooling, UV depletion. This leads to massive global famine as the price of food increases, making them inaccessible to population already vulnerable to food pricing, mass starvation on a global scale. So that's not a very nice way to end, but nuclear weapon, when we talk about nuclear weapons, there's nothing really positive to say about it. So that's where I wanted to end. Masco, back to you.
Yeah, thank you very much, Ferenc. That was a very uplifting, very interesting, but a very comprehensive lecture. Thank you so much. So I wanted to ask some questions, or maybe do some conversation. This is very interesting, especially when you talk about nuclear winter. Even those small exchanges of nuclear weapons may lead to such a horrible situation. Then during the Cold War, we have witnessed more than 2,000 nuclear weapons testing, right? And including atmospheric testing and underground, undersea testings. So is it fair to say that, of course, 2,000 nuclear weapons testing, especially the huge 15 megaton testing, or much, almost 100 times bigger than Hiroshima bomb. Both the United States and the Soviet Union used hydrogen bomb for the testing. So is it fair to say that we have already received so much negative environmental impact of those 2,000 times more than, no?
No. So this is a very different type of effect. If you have one, let's say the Tsar Bomba, which was a very, 68 megaton bomb, this would not produce this type of effect. Think about it in terms of what I talked about in terms of the blast wave itself not being, 100 times more than the effect, something like this. If you had, this is really modeling what would happen if cities would be collapsed, if you would bomb, and you're modeling over distributed areas. So you're not just looking at one test or something like this. You're modeling over what would happen if cities would start to burn and this kind of stuff, and it would be more distributed effect. So it's different from that point of view, from just having one test or even a salvo test where you have one or two tests. And also, much of that testing later on, of course, was done underground, so you don't have that kind of you don't have the same kind of effect where you could get things burning. And also, these nuclear tests are done in areas where which tend to be in areas which are more isolated. Of course, I don't want to discount that people are living in certain areas and they got a lot of health effects and so on, but they tended to be in areas which are more isolated, and things like grass isn't there to burn, or that you would produce these massive super fires. Does that make sense?
Yes, definitely. I thought so, but when we hear the 2,000 nuclear testing, people may get, maybe misunderstanding.
Yeah, that's a good point.
To understand there is a huge difference between testing and, of course, very different.
Yes.
So, having said that, it is also important to understand the serious environmental effects that happen in Semipalatinsk and also Marshall Island.
Yes.
And that's why people in Marshall Island were suing those nuclear weapon test states. But if I understand it correctly, the International Court of Justice basically dismissed that case. I think I need to follow this, but that was very interesting movement, although it was maybe didn't bear fruit as they wished, but at least that really raised the awareness of the nuclear testing and the damage that was caused by nuclear testing. So
yeah, and this is just to say, the effect for the Marshall Islands was very dramatic. Not so much in terms of, of course there's the radiation side of it, but also the fact that they had to move from an area where they lived, and then had to move, and then I think they were moved back, and then they're moved again, right? So,
yes.
So that's another aspect of this is for them, the fact that they had to move, and all the cultural things that they were used to, they had to live in a different areas. That was very difficult for them, and
Yes, and I also understand that those people, the indigenous people, were impacted. Their health was impacted.
Yes.
By radiation, definitely.
Right.
Yeah, this is rather very controversial history of the U.S. military, U.S. nuclear weapons, but another important aspects to look into. Then I think it is very interesting to learn that you mentioned the burst wave effect is not linear. And this is very, it's a little bit tricky. And some people, including myself, I thought if it's a 15 megaton bomb, this should be 1,000 bigger than 15 kiloton.
Yes.
Especially when we often talk about the Lucky Dragon incident.
Yes.
The Castle Bravo test.
Yes.
That happened in 1954. I think John Dupree is going to talk about the Lucky Dragon incident in his lecture tomorrow. But that bomb was the first hydrogen bomb, and it was I believe it was a 15 megaton, which is I think 100 times bigger than Hiroshima bomb. Kyoto.
Yeah, you're right.
Yeah.
You're right.
Yeah. So this comparison, I really believe that it's important to understand the impact.
Yes, there's another reason for that is that was one of the first testing that we're doing with, I think that I'm right about that, with dry fusion fuel. And they didn't account for a particular effect. So the yield was higher than they expected it to be, which was one case. If I can just take one moment, if you don't mind, to explain this a little bit better, or
please
more.
Do that. I wish, I would like to hear that.
Okay, so you have to really think of this as a balloon filled with small balls. If you think of a small ball representing 10 kilotons, right? 10 kilotons of energy. The small ball has a certain size in terms of the effect. So let's say we're looking at the effect of buildings collapsing, right? That would be, 1 kilometer or something like this. So that's the size of the ball. Now, if you have 100 balls, right, that's going to be equivalent to that 1 megaton, right? So you have 10 kiloton, 100 times 10 kiloton is 1 megaton, right? So if you have, so that's the total energy that you have. It's 100 times more. So really what you have is you only have 100 of those little balls. So if you think about stuffing 100 balls into like a balloon or something like this, it doesn't expand out that fast. It expands out slowly because you got to fill all the little areas. Do you see what I mean? So that's why the effect is not linear. It's not like you're putting, if you would put 100 balls all side by side, then that would expand out very fast. But you got to fill all the area in that balloon to have it expand out. And the analogy there is that the radius of that ball, of when you stuff those 100 little balls in there, that radius is the same effect. So there's the effect of columns falling or something like that you would have for a smaller 10 kiloton bomb being that radius. Does that make sense?
Yeah.
So you can actually prove this in the physics way, but I think this is very intuitive. Kind of think of it in terms of little balls, stuffing them into a balloon or something that's allowed to expand as you stuff in more balls.
Mm-hmm. Yeah, thank you. That's very helpful to me.
Good.
Yes. So could you, I also, you explained very well about the residual radiation versus the residual radiation, because we often hear that some people are saying, why people in Hiroshima were able to go back to the city so quickly, and some people wrongly understand Hiroshima is still radioactive, which is totally wrong.
Right.
And then compared to Hiroshima, unfortunately, Japan has a Hiroshima, Nagasaki, and then Fukushima. 5 years after the Fukushima, almost 100,000 people are still, they cannot go back to their hometown. So this kind of like a contrast. Like the people, I think for lay people who don't know very much about how radiation works, it's a very, very serious question and important question. So would you please explain
Yes.
one more time?
Okay. So you have to think of it this way. Once an explosion happens, now let's talk about a fireball. So a fireball happens like 500 meters or something above the ground. So you get this Mach reflection and you get this multiplying of the waves and you get this, strong effect. So what happens is it's very, very hot. It's giving off all kinds of neutrons and gammas and so on, but it can't penetrate the ground as well. It can penetrate the air, of course, but it can't get to the ground. So you can't induce, rocks or something like this. So that's the first thing. Now, it's very, very hot. And just like a hot air balloon, it moves very fast upward. And as it moves further upward, it then even more the neutrons and so on, the gamma rays can't penetrate and get to the ground where they can irradiate people and hurt people and so on. So because of that effect, the damage in the ground is not as dramatic at the hypocenter, where in Hiroshima. However, you still have a lot of radioactive fallout and contaminants because it's the fallout that is the radioactive isotopes. And these are the ones that produce the bullets. So that material just goes up into the air and that can travel over very long distances and get carried on winds and then fall somewhere else. So that means that somewhere else is going to be very highly contaminated. Not necessarily exactly at Hiroshima. So you have the two effects. The first effect is that this ball moves very fast upward. And so the radiation really can't reach the people down below. It's also, another thing is the fact that you have the blast wave, which is so dramatic, it will kill everybody below. So even if anybody would be there, they would have already been, even if they were irradiated, it's the blast wave that would have killed them. So that's why the effect is already less in the first place. But because this ball is moving upward so fast, those particles also can't reach the ground. And it's the radioactive materials that travel for a very long distance and then slowly, fall to the ground where you get the damage. Does that make sense?
Yes.
And so you talked about Fukushima. With Fukushima, of course, it's a very different in terms of degree. What happened is the radioactive fallout, had a certain pattern where wind was changing and so on, and it moved in kind of a 90-degree form, in a kind of shape. So that's really the fallout, the radioactivity that's there. It's a little different in that sense.
Right. So the Chernobyl is also the same as Fukushima.
Yes.
I see. Okay. And I also could you please go back to that effect of a nuclear weapon chart? You create a beautiful chart, so many different. I think this is a very, I really think, important chart that people, especially students who are going to study this year's topic, very important. It's very interesting and important to understand what's a comprehensive effect of nuclear weapons use.
Yeah, and out of the humanitarian conferences of nuclear weapons, there's a lot of interesting research. I kind of mentioned this on emergency response, on what would be our response to a nuclear event, which, if we think about very serious earthquakes that happen, for example, in Haiti, then, response isn't that fast as you would like it to be and isn't as comprehensive as you'd like it to be. And then on top of that, you got to think of people would be sending, emergency workers into areas that are going to be irradiated, and governments might not like to do that because it's dangerous for them. So there's all kinds of aspects to this that really haven't been researched enough, and I think it'll be very good for students to look at all these different effects. Even talk to people who have done some of this research at the Norwegian Radiation Protection Agency, for example.
Okay, great. Thank you so much, Ferenc. I think I don't have any more questions at this moment, but if maybe students or teachers may have questions, I'm sure they have questions. This is a very challenging topic, but it's so important to understand the effects of nuclear weapons. And like me, many people have some wrong understanding of the effects of nuclear weapons, like a difference between testing and actual use, and there are so many elements we have to understand. So teachers who are watching this video, if you have questions, please feel free to contact me. Then I will send all the questions to Ferenc too. So please feel free to ask any question if you have. So Ferenc, thank you so much for your excellent lectures, and you're always so helpful for this CI project. So thank you so much.
No problem.
Thank
Bye.
you. I will stop.